It's
Talk back to her.
it's great to see such a great crowd here. And can anybody really in your living memory remember a November 2nd in Iowa like this? Not me. Of course, I can't remember much, but this seems unusually good. Well, our speaker today, whom I'm going to introduce by his correct name, wants me to get to it, so I'm not going to review all his credentials. We know they are many. Dr. J.R. Paulson is here today to talk about this thing called the Golden Cut 2, and spoiler, what is the world's most fascinating number? It's phi. More than that, I can't tell you, but he will. Here's some reminders. Masks are welcome but not required. Please turn down your cell phones. Turn on your T-coils. Questions might, well, we're going to see, but in any case, probably they're going to come at the end. Probably Judy and I are going to carry microphones around to you, and if you'll speak right into the mic, that'll help our recording situation. If you care to donate for your beverage and cookie today, about $2 would cover the cost, and we appreciate that very much. And we're also really glad for all the help we've received piling up chairs afterwards, if you can, and but no more than 20 on a dolly. And with that, Dr. Paulson.
Okay, thanks. Okay, can you hear in the back? Fergie, is this volume good? Okay, well, this is a piggyback on the class last week. We talked about our address where we are in the universe. Today I'm going to tackle a couple of easy questions. How does the universe work? How is it constructed? Why do you hate math if you do? Was God a mathematician? And what's the world's most fascinating number? And we're going to cover all those today. Isn't that exciting? To figure out how the universe works, we have to observe it. But to do it correctly, you need to have accurate and mutually agreed upon units of measurement. These must include both distance and time. You also need math to quantitate and formulate any relationship that you find. So, are you ready? This may be the reaction of some of you. Or, more vociferously, why do I hate math? So let me see what kind of audience I'm dealing with here. How many of you, raise your hand, have taken algebra at some time? Geometry, calculus, post-calculus, differential equations, number theory. Oh, we got a few good hands going up. But you can see I'm not speaking to the choir here as a whole bunch of math lovers, right? I love the typo you got in this. We hate math, says 4 out of 10, a majority of Americans. Oh, wait a minute, 4 out of 10 is... So I'm going to digress here for a second. There's a whole bunch of reasons maybe we don't like math, or you don't. Some students, because they think it's boring. They have difficulty remembering all the equations. You can have a lot of mistakes. Fear of being humiliated or criticized. Many people are taught as children that they don't like math. We can't argue math. This is why politicians don't like it. You're either correct or you're incorrect. End of statement. Because it's not very creative and always follows the rules. Similar to learning a new language. Always says, we will never use it in our lives, so why do it? Or it can drain you, just using all that brain power. And maybe it's cool not to be good at math. And because the majority of people had terrible math teachers. I think that's the crux of the problem. Because most people don't get it. Well, I'm going to hope you get it today. I went back to my yearbook last couple days ago and took a picture of the Mu Theta Phi, or the National Math Club. So this is out of a class of 3,600 in my high school. This is the math club. there were quite a few women in there, outnumber the men, which I thought was interesting. And this is a ski club. They don't all even fit in there. So why do we learn math? For calculation. You want to figure some stuff out. Okay. Application. What are we going to use the math for? Engineering, building things, whatever. And inspiration. And I'm going to spend most of today hopefully inspiring you. How many people have seen this movie? Raise your hands. Great. If you haven't, see it. If you've already seen it once, see it again after this talk. It's true. It's great. It'll make you almost like math. But you'll be really impressed with what these black women did. And it's based on a true story. In 1962, these three computer women, Mary Jackson, Katherine Johnson, Dorothy Vaughan, hired at Langley to help get us into space and John Glenn to orbit. And this is what happens, but it's the plot, and I'm not going to give it away. Astronomy, meaning the word astronomy is derived from the Greek. Astron, meaning star, and nomi, which is derived from the word law or culture. So astronomy is the law or culture of stars. It's one of the earlier natural sciences. And why do you think Stonehenge was built? Not just a bunch of rocks that look pretty, but to make some astronomical positioning and predictions. Babylonians, Mesopotamia, were very big in early astronomy. Likewise, Jaipur in India, all sundials in trying to quantitate time and measure it. Of course, we did it. One of the reasons is to form a calendar. And you can see some of the early calendar. This represents the 12 signs of the zodiac. The Egyptians were pretty good at astronomy. And a famous one was Claudius Ptolemy. And he printed, I think, a 12 or 13 volume analysis of the stars and the planets with all the data in Alexandria in about the 2nd century from Alexandria, 13 tomes. And as you can see, he learned a little math from the Greeks, had some geometry, and tried to calculate a lot of the positions of the planets. But his theory of the universe was, of course, at this time, pretty Earth-centered. And we know that did not change till Copernicus. The Mayans were pretty good astronomers. Take a look at this observatory, the ruins which were there. They really did a lot of heavy, serious observing of the stars, and particularly the moon and Venus. They could predict eclipses of the sun. Of course, when the Spaniards came in, they just trashed all of the things that they found. But the Mayans were way ahead of time, as were other cultures, such as China. China were also good star watchers. One of the most famous ones in Europe was Tycho, a Danish astronomer, who built a pretty cool observatory at Uraniborg. And he had all these observatories, and he just get all the measurements and calculations of the stars. And I mean, he didn't have modern instruments, but he collected a lot of data. And his model, the Tychonic model, as you can see, is, gee, everything kind of goes around the Earth. The sun goes around, but Venus and Mercury go around the sun, but that circle goes around the Earth. The Hindu Arabic number system uses 10 for the digits, was developed in India and used by the Arabs. And the symbols were basically in the West by Leonardo, not of Pisa, Leonardo of Pisa, not of Vinci. And this book called Liber Abaci in 1202. It's kind of an important date for you to remember. And the advantage of this Hindu system is the first one that does number notation. So he worked in the ports there with his dad in customs. So imagine this boat's coming in there, and you got all this cargo, and it's all written down on these logs, and it's all in Roman numerals. Roman numerals, casks of wine, pottery and this, and then he's doing this, and how do you add these giant Roman numerals? Ever tried to multiply or divide a Roman numeral? Doesn't go well. So he was able to translate from the Arabic into the numbers that we use today. Side note, when I was in Russia in 1990, still the Soviet Union, and I was buying film in the gum department store off Red Square, the biggest department store in Russia, and the gal was using an abacus, 1990. So even before the Common Era, they were doing measurements. How far away is the moon? Well, Aristarchus said if I hold this coin up and it's about this big, and then the moon is that big, I can do a little math and I'll come up with 247,000. That's not too bad. Tomley also calculated the distance to the moon. He did it on eclipse, and he did it from taking measurements from two different places on the Earth, separated, Alexandria and over in, I assume that's in Greece, but I don't know where that is. But by measuring the difference in these angles of the different places during the eclipse of the sun, do math and come up with also some pretty good distances. Well, what do we do today? Well, we go to the moon, we put a reflector on there, and we shoot laser at it and bounce it back. And we can tell time, distance, how far the moon is away. So what's the universe made of? Well, Aristotle said fire, air, earth, and water. That held sway for a long time. He did add, however, a fifth element was the ether, and that was what was around, that's what's out there in space. Hindu and Japanese also had some of the same one, but they were a little different. You know, fire, earth, water, they had metal and wood. And they had a system of not only medicine, but of theology was all evolved around the interactions of these properties. You chemists in the room, and I think some of you know who you are, this would be an excellent bucket class, the periodic table of the elements. So there are 94 naturally occurring elements and another 24 that have been created in the lab, about 118. And now, I don't know how many there are. Somebody can probably help me. It might be 120, 124. Some of these only live a few microseconds. And do they get counted? Somebody said there's 126. I don't know, but we'll just say 118 for now. Now, you start up here at the top. Hydrogen, number 1. Helium, number 2. Lithium and beryllium. When the universe Big Bang went off, the first 20 minutes of the universe, guess what was formed, folks? Mainly hydrogen and helium and a little bit of lithium and beryllium. And what did I tell you in the last week's lecture? A lot of these others came, and carbon and all the things that we needed, carbon for life and iron for our blood, all these other ones out of supernova stars. So evolution of stars had to produce these other elements. Now, when I was a kid in high school, I didn't have to worry. Physics was pretty easy because you had protons, neutrons, and electrons. I can remember the charge on those, and that was pretty easy. Well, if we asked our physicists in the row here and say, well, wait a minute, what are the elementary particles now? We got quarks, and they're up, down quarks, bottom quarks. We got leptons, we got Higgs bosons. Holy geez, where did all these things come from? And I'm not going to digress on that. But as we drill down to try to find out what the universe is made of, it gets smaller and smaller, it gets more complicated. So math, along with more accurate measurements, allows us to formulate relationships and laws that help describe and explain the workings of the universe. So we're finding out what it's made of, but how does it work? Well, one of the first formulas that all of you even know, remember this one? What's that called? Pythagorean theorem. Square of the hypotenuse is the sum of the square of the other two sides. Later, our famous astronomer Kepler, Danish, he used the data that Tycho did and had to come up with math and figure out how to explain how the planets go. And he said they don't go around in circles, which everybody thought before. That was screwing everything up, because they don't go in circles. They go in ellipses. And they go different speed where they are on the ellipse. So they go faster when they're close to the sun and slower up here. But this area is the same. And you can likewise figure out some more math about how far away from the sun what your orbit will be. Pretty good breakthrough. Newton, laws of motion. You don't need some physicist to tell you what happens with your grocery store if you run into something. The groceries keep going forward, right? Gee, a law of motion. Or a patient I had 2 days ago, he's driving through, a dump truck hits him. Did not go well. Force times mass and acceleration. The dump truck had a lot of mass. Third law, action and reaction. But you got to put them in mathematical notation. And so Newton's laws, again, math. Calculus, which intimidates a lot of people. And I'm not going to even try to explain calculus, but it's the fundamental theorem for things that are changing. If you have this mathematical expression and you know what's happening at one part, you can predict what's going to happen at the other, and it was just so useful. And the first use of it was Isaac Newton. He used it to help come up with the law of universal gravitation. And so he's sitting there, and apples are falling on his head, and he's going, "Oh my God!" And he tweets, "Ha ha ha!" And so, what's the formula? Those of you who've seen this before: force equals a gravitational constant times the mass of the two objects, and inversely proportional to the square of the distance. So the farther away they are, the less the force is. The bigger the mass is, the stronger it is. And gravity is actually a pretty weak force. And what's this gravitational constant? Well, somebody had to come up with that number, and it's agreed upon. There's this science society for science and technology. Well, that number's got some wiggle room. And this chart shows what it's been since way back in the 1900s, what they thought different values were through time. And see, they vary quite a bit, the gravitational constant. And then up here, they're getting a little closer to what they think it is. However, planetary motion, some of the planets, Mercury didn't quite go the way it's supposed to go, and Mars didn't quite go the way Newton said it was supposed to go. Well, in science, if you got a theory and it doesn't completely explain it, you better think of something else. So get rid of it. So Einstein comes along and goes, no, gravity isn't a force. It has to do with space and time. And the shape of space and time, you go, wait a minute, it's a force. It's like magnetism, you know. No, Einstein said, no, you guys got it wrong. So I'm going to come up with this new formula for you, and this is going to explain gravity and how it works in space-time. So you go, well, okay, Einstein, how do we know you're right? So one of the first things was an eclipse of the sun. And during eclipse of the sun, you could see stars behind the sun. And the star, you know where it is in the sky, but then you go like, well, wait a minute. The light was just, anybody know what happened on that one? Restarting. Okay, Bob. So I'll continue talking. Hopefully it's going to restart where it was. The first thing that happened was they found that the light was bent. So then later, Hubble Space Telescope looked at a star, and it's supposed to be there, but they looked at it real close to another star and found out that the light is bent. They did that again. And then Cassini Space Probe, when it's out by Saturn and sending waves back to the Earth, they find out that, gee, it's also bent. So Einstein's right on the money with that. That was part of his general theory of relativity. So one of my next slides would show that we'll come up with, is his special relativity. He wanted to look at the relationship with mass and energy. And he came up with the famous, what's that formula? E equals mc squared. We all remember that. Yep. So, keep going. Getting close. Go farther. Farther. Keep going. Okay. I'll take it from there. That's good. Good share. I don't know what I went bye-bye. Okay. So again, the bending of light, proving Einstein's theory. Also, Einstein at that time said, there's got to be these things, according to my math, called black holes. Nobody sees them, those don't know what they are, but there are these things, and light doesn't escape from them, and all these characteristics, and you go like, remember, this is almost 100 years ago, folks. And so recently now, with the Webb telescope and the Hubble telescope, you see those big arcs. Yep, that's light being bent by galaxies, gravitational lensing, proving again Einstein was right. Not to be outdone by the Hubble or the Webb or Einstein. I was out a couple months ago when trying to find gravitational lensing myself with my just an hour exposure, and this arrow was pointing to this little thing here that looks like, well, it's not like a star. That's a gravitational lens. So I have proven Einstein correct. His famous formula with EMC squared. In graduate school, I used to like this formula. I think you guys tell me if it's a Lorentz Fitzgerald formula. And some of our homework assignment was if a 100-gram mouse is sent on a spaceship at 99.67 the speed of light, how much will the mouse weigh? And you go, the mouse weighs more. And you go like, whoa, exactly predicted with Einstein. Or an astronaut goes up and goes in the space station. It goes around the Earth so many thousand miles, and he stays up there for 4 months. How much younger will he be in comparison to you when he comes back? And you can figure that out. So, yeah, he's younger than you are, predicted by Einstein. Another one that we all know, a law, things that you heat up, cool off if you leave them on the counter too long, right? Well, there's a law involved in there, folks. Second law of thermodynamics. You may not care about it, we understand it, but it has great implications for the universe, because it means eventually the entropy says everything is going to kind of cool down. So sometime in the distant future, the universe is going to be cold and dark. It's all going to be the same temperature around there, so I'm not worried about it. Schrodinger, equations for particles. What does a subatomic particle do? And we got our great quantum physicist, Dr. Case, and with this hat on that says, what, Bob? Drink coffee, then quantum mechanics. So if folks drinking coffee, then you do quantum mechanics. And so, again, another model for what happens at the subatomic level with quantum physics. What's going on with all these particles? Formulas have been made that try to explain that. And most of them are pretty cool and good. So we've come a long way in trying to decipher the universe, and I think we've done a pretty good job for some primates that are really not that far out of the jungle in the big picture of time. So what about the special number that we talked about that ties the universe together, that talks about sunflowers and spirals and galaxies and rabbits? I love this quote. So if you remember one quote from this, try to remember this one. When you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. Lord Kelvin. But you find out there's a lot of truth to that. So, hence, the other part of my talk here is getting into the golden cut, the story of Phi, not pi, the world's most interesting number. Some people think it's actually a divine number, and that's the Greek symbol for it. Or, is God a mathematician? And this famous picture, God the geometer, says it all. So this is my hypothesis that I'm going to use. And it looks a little wordy, but I do want to go through it because I'm trying to set it. Just as Prometheus gave man the gift of fire, pretend you were an omniscient architect and mathematician both. And some deity comes to you and says, hey, I need some advice on building a universe. And the deity's going to need help in the design of matter, from atomic to sub-microscopic levels to the structure of galaxies made up of hundreds of billions of stars. But he'd like to rest on the seventh day, so that a repetition of scale, similarity, and maximum efficiency should be preserved. He will need to create a myriad of plants that will all have serious issues of leaf, petal, branch, and seed design. How do you keep them the same as well as allow them to grow in an especially tough problem? Can a similar template be used in the animal world? The deity would consult the supreme physicists and chemists for details also on the exact composition, timing, layout, and the grand unified theory, as well as a few laws to keep the whole thing running on its own. Moreover, even though the supreme deity is nearly omniscient, math is not his forte. So the number of formulas shouldn't be too complicated. So your challenge is to, here, I'd like to help you out, deity. I'm going to give you a number. Hidden numbers and hidden proportions. We're all familiar with pi, 3.1415, the ratio of the circumference of any circle to its diameter. But less known is phi. Some people pronounce it phi. I was a fraternity member and I call it phi, which is why even more fascinating. So if asked what the petal design in a rose, Salvador Dali's painting, Sacraments of the Last Supper, a beautiful spiral shells of mollusks, breeding of rabbits and spiral galaxies have in common, you might be hard-pressed for an answer. But the number that unifies them is also related to a geometric ratio known since antiquity and recently discovered again in quasi-crystals. The divine proportion. A book published in Italy in the 16th century went even so far as to call it divine. And it's continuing to fascinate many since. In 1923, the poet Edna St. Vincent Millay wrote a poem entitled, Euclid Alone Has Looked on Beauty Bare. She really liked math, and she really liked geometry, and she was a poet. Was she onto something? Are there aesthetic principles of beauty based on mathematical formulas? And a corollary question, are mathematical expressions the real underlying beauty as Plato and the Pythagoreans claimed? Math in the cosmos. Another question to ponder throughout this class is, what's the relationship between mathematics and the universe? Was mathematics discovered or invented? Does it exist out there, independent of humans? Is it truly a creation and an ordering that we see or impose on the world? Would other beings on other planets come up with the same formulas and rules, or would theirs be totally different? There's some ideas to ponder as we go through this. The divine proportion. Geometry has two treasures. One is the theorem of Pythagoras, and the other, the division of a line into extreme and mean ratio. The first we may compare to a measure of gold. The second we may name a precious jewel. Again, our astronomer friend Kepler. So Euclid lived in Alexandria and a couple hundred years before the Common Era and did a number of books called The Elements. I can't remember, 6, 7, or 10. But he was the man. And in it, he said, let's just take a line. And we're going to cut it in what we call extreme. We're going to put a line in it where C is. But where we're going to put that line and divide it is going to have the same ratio from this big long line. Ratio to this longer segment is the same as this longer segment and this segment. So they're going to have that same ratio. And this is most of the math that you're going to get here. Fortunately, it's not too complicated. But if you algebraically solve it, you come up with a formula, and it gives you this number. Well, that's interesting, but it's rounded off. So that means it's not an exact number. So what does that mean? There's irrational numbers. What does that mean? They're crazy? No, they can't be represented as a simple fraction. Important property of these irrational numbers. the decimals never repeat. You're never going to come up with the same number. And it never ends. It goes to infinity. So as examples, what's the square root of 2? If you've ever done that in math, or 3 or 5, or pi, or phi, it just keeps, how many decimal points you want to go to. And in the number world, they're rational or irrational numbers, and this letter phi happens to be an irrational number. Okay. Mark Barr, an American mathematician, gave it the name of phi, this ratio, after Phidias, the great Greek sculptor who lived around 490 to 500 BC. So what you do is, you want to make this, you take a square, bisect it in half, take a long diagonal up to this corner, and then you just take your little protractor and you just square around there. And you get this length. Okay? Well, what's the ratio of this side and this side? And we find it is phi. And that is the golden ratio. Well, what happens if you continue the process and you got this, and then you make another golden rectangle, and then you make another golden rectangle here, and then another, and then another. You get all the sequence of golden rectangles, all from this one starting point. And when you draw intersecting lines here, they all intersect here. That's kind of cool. What's a golden triangle? You're going to hear the word golden used a lot today. This is a triangle where it has the ratio, again, of the side in the base, and we want it to be phi. Well, if you do that, you come up with the angle up here is about 36 degrees. So that's called the golden triangle. Well, what's so cool about that? Well, gee, if you do the same thing, you have the golden triangle, and you go up here, bisect the angle, and then connect that, and then you bisect this and go up here, you get another triangle, and you go up here, and these triangles are all exactly golden triangles. So you can keep going on ad infinitum with these golden triangles. And you go, okay, that's kind of cool. What about a right angle triangle? Well, you can do the same thing with that. And if one is the base, the ratio of this side to get phi, it's 1 in the number phi and phi squared. That's how you do with right triangles. What if you take the triangles and you connect these here? Yes, you get this spiral, and it kind of goes all around. That's called the golden spiral. You can do it with the squares. Rectangles we had. So you take your template of your golden squares and you connect. Gee, that's the same curve. So you can make this golden spiral, golden triangles, or golden. So this is what a spiral looks like, called the golden spiral. Contrast it to the spiral of Archimedes. So there's a couple different spirals. This is like when you did a rope and just coiled it on the floor. And Archimedes is the one that gave it that name. But what is interesting about this triangle or spiral is very different. So any place you want to draw a line here, you draw a tangent, any place, I don't care where you do it, just someplace draw a tangent to it, and then connect from the eye of God, the center, and then measure that angle. Connect over here, measure that angle. Go up here, measure the angle. What do you think you find? They all the same. Every place on that spiral, the angle is the same. So it is exactly following a curve that the angle. So it's a self-similar spiral. Often appears in nature. It's also called the logarithmic spiral. And other people have been familiar with it. We'll come back to that in a minute and see where it's in nature. Pentagons and pentagrams. they were pretty popular in medieval times. And so what's so fascinating about those? They're used for the Freemasons, symbols in the occult, and the pentagram is used a lot with the body. But if you look at it, you find out, oh, that's an interesting ratio in there. You see this 0.618 in the middle of there. So you find that these pentagrams have some interesting relationships. Oh, you're seeing phi again, phi squared. So all these constructions of the pentagram have the golden ratio on it in phi. And they knew that there's pretty interesting stuff going on with that. They didn't know what or why. And look at the different things you can construct. And when you play around with it, here's your pentagrams and big pentagrams and little pentagrams, and oh, geez, wait a minute, 36 degrees, that's a golden triangle. You mean so you got golden triangles in here and these pentagrams, and can go on, and you go like, well, that's pretty wild. So what do all these golden figures ratios have to do with art? Is there an innate aesthetic to the golden rectangle? So if I did a group in here, which I don't have time, and I say, which one of these do you like better? Well, I'm not going to use the word beautiful, but which one of these gets you in and you like a little better, and have you vote? This is how people vote. They like a certain one better than the others, and a second one, and then after that it's downhill. Well, if you measure those and those triangles and find out where it's the most popular, gee, what ratio is right under there? Phi. So people have no clue about what we're talking about. I like that. I like the shape of that rectangle. Hence, what is your Visa card shape? What is the National Geographic magazine shape? What's your Kit Kat that you shouldn't have any left over look like? Okay. What does a good-looking egg look like? So what am I talking about? So if I say, what's a cool ellipse look like? Draw me what you think is the most beautiful eggy ellipse. Well, they do that, and they have people, and gee, what percentage? The highest percentage of the ellipse has to do with the axis of that coming up with phi. So there's something in people that are looking at that and going, that's interesting. So the ancients have been fascinated by this too. So Vitruvius wrote, without symmetry and proportion, there could be no principle in the design of any temple. That is, if there's no precise relationship between its members, it's in the case of those of a well-shaped man. So he's comparing architecture to a human. So, the font of the Parthenon, there's a certain ratio in there. Other buildings. I saw a picture of the United States Treasury, and the thing, I haven't given this paper, I'm like, wow, that looks just like a golden rectangle. What about the Egyptians? Did they build their pyramids? Anything to do with this? Well, first of all, you got to think that's several thousand years before the Greeks, before the golden ratio. But people are trying to come up with, cubits, and they're saying, the Greeks probably did it, and if you had the pyramid and the size of the earth and the moon, and this is, I think, it's been shown overuse of trying to call this a ratio. What about the Vitruvian man? Here's the quote from Da Vinci. Put a man on his back, put his arms out, and you will find that there's certain proportions that he has. And we've all seen this classic. And so, in the human form, he's finding relationships. And the navel to the floor and the navel to the top of the head, kind of comes out pretty close to the golden ratio. That's kind of neat. This is the architect, Le Corbusier, last century, and he tried to get a whole system of architecture based on these ratios of the human body and tried to design architecture and things. So really took it to an extreme. Was the golden ratio used by famous artists? A couple artists went to the in London to the National Gallery and said, mathematician and psychologists and started looking at some of the paintings and said, gee, we looked at this and the size is a golden rectangle, and draw some angles in it. And so going back and looking at art, are there golden rectangles in these or not? And this one by Botticelli, someone's even gone and got ratios written in phi on the side. Maybe yes, maybe no. I'm not a photographer, but I didn't know the golden triangle rule, rule of thumb in visual composition in paintings or photographs, especially those with elements that follow diagonal lines. Gee, there's something to be with that, say with that. Before the spiral was put in here, I'm wondering, why did they put that woman where they did, whoever it was? Why did they stick her up there in the left? But if you superimpose a golden spiral, what's it right in the middle of the golden spiral? I don't think any coincidence there. Salvador Dali, Sacraments of the Last Supper. He's not so subtle. He's got Euclidean geometric figures in there, but in the dimensions are all. And any of the great artists had to have and did have perspective to make the thing look the way they're supposed to. Geometry, lines, this is the point of focus. So the great artists knew math directly and indirectly. So we're going to just briefly introduce our Fibonacci, but this might be a good, how close are we for break time? Okay, so we've talked about the golden ratio, then we're going to talk about Fibonacci in the series. So let's take a little break and reconvene in about 5 to 7 or 8 minutes. Okay.
Yeah, if
Come back
Dr.
a couple
Paulson
minutes early,
has
that'll be good.
so much more to say that if you look at this clock, we're going to start at 10 up, which is about an 8-minute break. Okay, get to getting. And I'll ring the bell if you're on to Leonardo of Pisa.
And we get the lights. Some more lights, thanks. Okay, now we're going to get into the fun stuff in this half. So remember, we've talked about him before, first person to translate the text and bring us the system of decimals that we use now. And this is the book that really changed Europe. Once he came up with this, they got rid of Roman numerals and we ain't using this anymore. This place system, base 10 is the way to go. So Fibonacci, which means the son of Fibonacci, came up with this, was sitting around, I don't know, he's bored, said, I'm going to come up with this series. And he says the series is going to be simple, and you can memorize this. There will be a test on this. So when you're done, you're going to have to explain the Fibonacci series. So you start with 0. That's pretty easy. And you add 1 to it, okay? Then you take those two, 1 and 0 are 1. Yep. Take this one and this one, add those together. Oh, that's 2. Take this and this together. Oh, that's 3. Oh, take this and together, or 3, 5. You get it? So I don't have to go on infinitum, but you can see how he does it. You go, okay, that's kind of cool. Yeah. So, but what you find out is if you continue to go on and on with that series, it starts coming down to some funky number here. And if you graph it out and say, well, what number are these points approaching? They never meet it, but what line are they coming to? And if you take it out to 400 decimal points, what line? It's the golden ratio. Well, wait a minute. Here's some numbers you're just adding up, and they come back to this thing of how you define a line. And it's phi. That's weird. Oh, let's go back to our golden rectangles and our golden spiral. And we say, well, what's the area of the square that you formed from this golden rectangle? Oh, 21 by 21. What's the square of this golden rectangle, the square of that. Oh, 13 by 13. Oh, 8 by 8. Wait, 5 by 5. Have we seen these numbers before? Yeah, so his series has to do with golden rectangles and spirals. That's pretty cool. And what about your golden triangles? Well, if you measure angles in that and take the ratio, which we're not going to do, but you find phi comes out of the woodwork. So, what about in nature? So this is all interesting. So Fibonacci himself said, let's pretend, just for fun, that you have some rabbits, and that you have a pair of rabbits, a male and a female rabbit, and you're going to let them breed. After a month, I didn't know this. That's why rabbits breed so fast. Every month, they can have kitty rabbits. So he said, after a month, the pair that they just have could breed and pretend they have a pair of rabbits, male and female, and pretend that there's no foxes, nobody comes around and eats the rabbits. So every month, there's a different pair. How many rabbits will you have at the end of the year? So Fibonacci is throwing this out to the crowd. And so, well, you can get your paper and pencil out and start drawing rabbits, and yeah, but if you're clever, you go back and you look and you see, oh, wait a minute, these rabbits, 2, 3, 5, 8, 13, 20, wait a minute, 144 after a year rabbits you'd have. And you go, wait, that's a Fibonacci number series. Oh, isn't that intriguing? Some of you in here I know have raised bees before. Well, in honeybees, there's different kinds. There's the queen, and there's the workers, and there's the drones. But the drones are made from unfertilized eggs. And so they don't have any daddies. They just got mamas. And so let's say you take bees, and you want to go back on the drones and say, well, let's look at your parents and your grandparents. Well, there's one parent, but let's take that back. And when you go back and keep going back on drone bees, gee, have we seen some numbers here that we recognize? So wait a minute, drone bees are doing this Fibonacci series. Okay, some of you that are of grandparent age, and your kids are bored and it's rainy, and you want to have them do Fibonacci math test. So you get the younger kid who can't go up too many stairs. Maybe the kid's size, they could go up one stair at a time or 2 stairs, but they're not big enough to go 3 stairs or 4 stairs. And you pose a problem to them. How many ways can you go up? And you pick a number of stairs, like 5 or 10 or whatever, by going either one step at a time, and I'm not going to demonstrate down there, or you can go 2 steps. Okay, pretty straightforward. So you find out, well, yeah, that's pretty simple. You go, 1 step, and at 2 steps you could take it all in one, right? Or you go up a little this step and this step, and the next step you could go blah 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 blah, or big step or big step, and you keep doing the stairs, and gee, what do you find out? The number of stairs you got, your kid's going to do, your grandchild is going to do, is Fibonacci series. So if you got 8 stairs, you keep that kid busy all afternoon. Because there's 34 different ways the kid can go up those 8 stairs. And have marked out on a piece of paper, because you don't want to forget that. So I thought that was kind of fun to do. Physics in the Fibonacci series. I'm not going to get into too much physics, but this is an interesting one. So let's not talk about rabbits or whatever. Let's say you got a couple panes of glass, and they're a little different, and they have 2 different refractive surfaces, but you pancake them together. So if you're a light wave, you come through, you could just shoot on right through. Or you could get to this interface in between, and you could bounce back. Or you could go through the first interface, but then the second surface, and you could bounce back. Okay? Now, or you could go to this one and bounce back, but then go all the way through. Or you could go to this one and bounce back and go all the way through. Or you could go this one and bounce part way back and go all the way through. You get what I'm saying? So if you do that with the light waves, not rabbits or kids on stairs, gee, what do you find? 13, 8, 5, 3, 2, 1. So these light waves, they didn't read this math text. They don't know how to do this, but they're kind of following this thing. Phyllotaxis. Remember our problem of plant design that I posed to you? We need not only to determine how branches and stems and leaves should be aligned, but how to pack seeds in the most efficient way. How can we maximize the exposure to sun, rain, and air? You don't want to have leaves right over one another. The bottom leaf ain't going to get much sun, right? So, you just put them out here? But then you only got a 2-leaf plant. That's nice, but what if you got more of them? How are you going to arrange them? When should you branch them? So this was studied by the Greeks 300 years before, called Phyllotaxis. He was, and the first person to discover a relationship with that, between leaf arrangement, was Kepler. Astronomer is getting around. So what you do is you measure on a tree branch when it sets out a branch here, and then it turns a little bit, and then the next branch comes out here, and you count how many rotations, how many branches come up to make a complete rotation. That make sense? Or another plant, let's say, is the sneezewort. Never heard of it, but anyways, when it grows, it comes up. Let's see, when should I send up a branch? Okay, here. Okay, let's send up another branch here. Okay, let's send another branch here. Okay, I'm going up here. I'll send up another branch here. And then I get up here. I'll send another branch. And you see the branching. And, gee, guess what the branching comes out as? Fibonacci series. Or again, branches on certain trees. Now, trees aren't all the same. But if you want to go out and look, you'll find out that elm tree branches 3 times around, cherry tree 5, pear tree 8. Why not 7? Why not 4? I mean, nature's onto something here, folks. Why is she picking these things? So leaf arrangement around the sides, leaves per turn, is pretty important. So you look down on it, and you can see that these leaves are pretty well spread out. So again, looking down on this, you see there's no leaf that's getting shortchanged, right, on light. But it also works for drainage in rain. And what about petal arrangement? You start looking at petals, passion flowers, and how many petals on there? Well, if you look at you see 5, okay? Buttercup, chicory, 21, daisy, 34. So if you want to do she loves me not with a daisy, you're going to pick off 34 before she loves me or not. So you can already figure that out ahead of time. So petals on flowers have different amounts of petals, but they're all Fibonacci. Okay, why does this daisy head have spirals that are in the number of Fibonacci series? So now we're looking at the petal pattern, and we're seeing it's spiraled, but these numbers. So imagine you're a rose, and you're a little tiny bud. You want to be packed in as close as you can, as many petals as you can get, so that when you open up, you got the maximum number of petals, right? So you can't just pack them any old way. Nature's figured out how to do it. And petals, again, a lily, 3. 5 buttercup, delphiniums, 8, plantain. Again, so different plants pick different number of petals to go around, but they all pick Fibonacci numbers. Okay, now why does the seed head look like this? It looks kind of like a spiral pattern. Well, how are you going to design a seed head? So remember, the deity I'm given say, how can you get the most seeds in this area of the sunflower? Okay, engineer math. Tell me how to do that. Well, packing, it starts simple. If you got square things, you put them in a square box. But seeds are round. So having hexagon patterns is more efficient for roundness. However, if you look at the sunflower seed, what do you see? I don't know about you, but I see a bunch of spirals going this way and a bunch of spirals going that way, don't you? Now, why does that occur? Nature has figured out that if you use this angle, 37 point blah, 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 the petal angles here, you can pack this many seeds in. Looks pretty solid to me. If you change that by 1 degree, add 1 degree, this is how many seeds you can pack in. If you subtract 1 degree, this is what the seed pattern looks like. So there's this angle. Gee, guess what it's called? The golden angle. That will allow you to get the most seeds for your buck. So some of us have coneflowers out in our front yard. You can take a look at the seeds on that. Some of you that live in the pine forest, take a look at some of your pine cones. Gee, you never noticed that before. Oh, a couple sets of spirals. Oh, well, you can number them all, and you can check them out, and you're going to find that they spiral, but you're going to come up with what kind of numbers? Probably Fibonacci numbers. 13 spirals that way. 8 spirals that way. Wait a minute, this is pine cone. This is different than flowers. Some of you pineapple lovers, hopefully after this class, you look at a pineapple differently. And you'll find out that, if you look carefully, there's some spirals going this way and some going this way in different angles. And wow, that's kind of wild. I think I'll count those. Gee, what numbers you come up with? 5, 8, and 13. So the pineapple has been reading Fibonacci. What about animals? There's proportions even in dolphins. We talked about human proportions. Let's pretend you're a ram and you don't want to be a buck. You don't want to be an elk and have horns that are going on. You want a horn, but you don't want it to keep going out. You want it to stay in place. Well, anybody know what shape that could be? Could be a golden spiral. Ever took an elephant tusk off and try to get the curve on that and find out where it is? Gee, that elephant tusk is part of a curve of a golden spiral. Fossilized ammonites are things from under the sea. Shells. Gee, look at that beautiful repetitive pattern in the shells. But the nautilus is, I think, visually the most interesting to me for presentation. So here's this nautilus. So it starts out as a little baby nautilus, and it's got a shell, and it grows. Well, that shell ain't going to keep it. It's got to have a bigger shell. So it builds a bigger shell. And it gets a little bigger shell. It can't live in the little house that was just in. It keeps building bigger houses. Well, it wants to not build weird houses. It doesn't want to build it in a straight line, or it's going to have the shell that's 10 feet long, and it's got to drag around, so it wants to curve. But if it curves too much, it's going to curve back on itself, and you're going to have an ingrown toenail or ingrown nail that's not going to go well. So, if you cut a shell in half, you see that's why they call it the chambered nautilus. There's all these chambers. Well, gee, what does that look like? Golden spiral that we just did in math. So all these lines, the same angle. So this nautilus is pretty smart. He's figuring out the best way to build the shell to keep the same angle. Okay, now let's change over. You're a peregrine falcon, and you're pretty fast, and you're going to catch some birds. But if you ever, they don't just go and, like I would just dive down and, just get that. No. Gee, they follow a kind of interesting pattern, don't they? What's that look like, folks? Golden spiral. Oh, why do they do that? Not stupid. So if I'm diving down here to bird, as I get closer, my angle is changing. I got to tip my head up. Then I get closer, I got to tip my head up because I got to keep my eyes on the target, right? Well, so my head's getting cocked up, and I got to keep changing my head angle, right? Well, what happens on these guys? to keep their head straight when flying because their eyes are on either side of their head. They need to cock their heads 40 degrees to take full advantage of their sight range. The spiral pattern allows them to maintain maximum speed while eliminating drag from a cocked head. So I can just get my head straight, not have the drag, and I got the same angle. I don't have to be making all this stuff. I get it on my cruise angle, and I'm going to do that. That's why they can go up to 200 miles an hour. What about in people? We already talked about the ratio, golden ratio in the human being. Yeah, I think this one's a little contrived. But they're trying to say the arm from here to here and this ratio from here to here, and then in the hands of the fingers and the digits that they have a golden ratio, and you got to fudge some numbers to get that, but it's kind of the point. What about the human heart? What's that have to do with any of this? So, the heart, all of us that have hearts are ventricles. It's the left ventricle that does all the pumping, right? So they did a study of 1,400 Swedish and Chinese, because they didn't want to get cultural bias in here, on the average ratio of the left ventricle, how wide it is to how long it is. And, surprise, they came up with this ratio. And what they found out with, if your heart doesn't have close to that ratio, and it starts getting wider, rather than longer, the farther it gets from this golden ratio, the worse it is as a pump. And it gets far enough, you're going to have heart failure. You're in big doo-doo then. DNA molecule. How does that get in there? Well, somebody measures them. Indeed, 34 angstroms long by 21 angstroms wide for each full cycle of the double helix spiral. Pretty close to Phi. And electron microscopy of the DNA, you find the spiral, and look at that on the right. It almost looks like something out of Euclidean geometry. And you go, wow, that's pretty, got symmetric angles and stuff. Gee, 10 pentagons. Okay, you're up in the space station, and you see Hurricane Ian coming down over Florida. This is an Ian, but it's another one in upstate New York. And you take a picture of it, and then what do? You get out your book, and you get a golden spiral, and the hurricane is following a golden spiral. Pretty neat. Or I image a spiral galaxy, the whirlpool, and I put a golden spiral inside the spirals. And what do I find? Or other spiral galaxies. Not all are spiral, but a lot of spiral when they follow it. And so there's some reason why this is going on. Okay, our last part that we're going to have is fractals and the golden sequence and the golden tree. Nature doesn't have a bunch of pentagrams out there and all these cool lines. Nature's got all these ziggy-zaggy things. So you go, wow, what's that have to do with anything? So fractal geometry is an attempt to describe shapes in the real world. Very few straight lines, not Euclidean geometry. So this man by the name of Mandelbrot created this term. The Latin fractus means broken or fractured. It's a central concept in geometry of nature and the theory of highly irregular systems called chaos. So is there any order in chaos? That sounds like an oxymoron, but actually there is. Fractals have the characteristics, if we look at them like any scale, it looks like the same. Matryoshka dolls that I brought back from Russia. You take this one doll, and there's another doll in it. You open that one, there's another doll in it. And lightning, river, lake shorelines seem to have actually a fractal pattern. So the self-similarity, like we saw in the Nautilus, is something that also shows up with these fractals. Now, another golden sequence. This is easy. Start with the number 1, replace 1 with 10, and then on replace each 1 by 10 and each 0 by 1. You'll come up with the following sequence. And that's what it looks like. 1, and you just follow that rule and the numbers you get. Well, note that the number of digits is a Fibonacci series. Notice that the number of 1s and 0s are 2. And the ratio of 1 to 0 approaches phi. But you can get the next number just by adding the two before it together. So you don't have to go calculate. Once you got a couple of these, you just add the one before it. Remember how we talked about Fibonacci series and went? Well, you do it with this, and you get these numbers. So you look at any place in that pattern, let's say it's 85 things long, any place you look, it's going to look exactly the same. Oh, different patterns can come out. So you take a triangle, and you put another little triangle on that triangle, and you get the next one, and the next one, and you build triangles on those, and this can go on almost infinitum. So all these different patterns are fractal shapes. And you can use pentagrams, triangles, or you can use solids, squares and triangles. And you can see how, when you kick them down, what you get. In architecture, people have used that in architecture. What about lightning? Lightning has fractal pattern to it. Certain kinds of cauliflower and plants, the repeating things. So each one of those little spiral things has another spiral on it, but it looks like the others. It just looks like the same thing. What about crystals? Amethyst on the left, pyrite. I need some of my chemists or physicists to talk about quasi-crystals. But these are crystals. Some crystals have a repetitive same pattern all the time, and others are just amorphous. There's no pattern. But these quasi-crystals are kind of neat because they have a shape, and boy, that shape looks kind of like a Euclidean pentagon. And when you do electron microscopy, you find patterns like this at the subatomic atomic level. Well, those patterns are pretty interesting. What about snowflakes? The ratio of the branches of a snowflake results in the golden ratio. So if you want to go out and check out some snowflakes, golden ratio. Okay, you got Great Britain. I say, what's the shoreline, length of the shoreline? You get a yardstick and you go, or a tape measure, go around. No, we can use fractal geometry for that. You go, what? Yes, mountains, streams, deltas, all can follow fractal geometry, even though they look like there's going to be no pattern to them at all. Branching. For many fractals in nature, from trees to the growth of crystals, their main characteristic is branching. You start with a stem of a certain length and it goes up, and then at 120 degrees it branches and it goes out. But what's going to happen if this angle is a little too much, or if it's too close together? What's going to happen? These guys are all going to run into each other, aren't they? So you're going to find out there's a certain angle that if you go, you can continue to build these patterns. So here's a couple of quilt patterns, and you start with this, and you keep going, and you're never going to screw up. It's always going to come out nice it is, but then the next would be smaller and smaller and smaller. It's called the golden tree. Just as our branching model can be drawn for squares and triangles, they can be done in 3 dimensions. So you got a drainage system, you got a circulatory system, and what is the factor where the branches go out? You get maximum branching, but they just touch. They don't overlap, and they're not this far apart, but they just touch. Like, gee, it's called 1/phi, which I find pretty amazing. For triangles and squares, you want to cover the maximum area with just touching. 1/phi. So even though it originated in the pentagram, the golden ratio, factual geometry is associated even in simpler figures. So, tree, what about in our own lungs? So we asked remember the gods, hey, give us mammals' lungs, but we want the most of villi we can get in a lung. What's the formula we should use to do that? Trial and error? No, let's use the golden branching ratio, and that's going to get you just what you want, Doc. Or a kidney. You want a nephron. You want to collect urine. Hi, what's the best drainage system for the kidney that you could come up with? Or the heart. Vascularity of the heart. You'd like the heart. Most of the heart to get as much oxygen in that you can with the circulatory system. Fractals in computers. Computers now can use fractals, and they can do incredible stuff. So not only can you just get all these really cool patterns, and maybe at the end, if we get done, I'll leave one on and show it running and how it just goes on, I consider, to infinity. And it's just incredibly beautiful. And this is the one that I'll show later. Conclusions. So we're answering our original question. It seems that phi is the ideal number we could pass on to the deity. It can be used on a micro and macro scale. It can maximize many biologic processes, from phyllotaxis to designing a lung and kidney, as well as controlling weather systems and keeping stars in order. And phi and its derivatives seem to minimize energy waste and encourage energy conservation in plants alike. That's why Darwinian evolution has happened. It didn't always happen, but the ones that didn't come up with this, they ain't around anymore. So how is it the simple division of a line in this mathematics series can be found in nature as well as art? And is this relationship in numbers, is it just out there and we just discovered it, or would he construct it? So now do you appreciate mathematics more? You can use it to calculate the time it'll take you to go to Chicago if you have an average driving speed of 72 miles an hour. Okay, that's good. But now we got our Google Maps, so you don't even have to do that. Now you know that mathematics, over 5 years of it, was used to create the first ever image of the black hole that I showed you last week. That was mathematically predicted 100 years early by Einstein. So he says there's this thing out there, and this black hole, and then you find it. It takes 5 years, and got 300 scientists all over the world, and they got all the data, and they got to spend 5 years cranking the math on it. A little different than driving to Chicago. So now you should be able to look at nature around you and not only see beauty, but have some appreciation of the relationships underlying it, from flowers to distant galaxies. And here's our black hole that was released 5 years after we got the data. Oh, we talked about the universe, what it's made of, the laws that run it, and of course the natural extensions. And well, where did it start? Where did it come from? And where's it going? Well, gee, we got an equation for that too, folks, that kind of explain that. And because it's accelerating now, it isn't just like a straight line acceleration. And that's where we come up with dark matter and dark energy and to do that. So, is God a mathematician? Kepler felt the golden ratio served as the fundamental tool for God in creating the universe. IBM mathematician Pickford wrote in his book, The Loom of God, and I love this quote, "I do not know if God is a mathematician, but mathematics is the loom on which God weaves the fabric of the universe." Galileo wrote, "Philosophy is written in the grand book, I mean the universe, which stands continually to open to our gaze, but cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, without which it is humanly impossible to understand a single word of it." Einstein, as far as the laws of mathematics refer to reality, they are not certain. As far as they are certain, they don't refer to reality. Quantum mechanics is a great example of that. Mary Seton, "I see a world order in the universe, and math is one way making it visible." Agree more with Roger Penrose. How is it that we human beings that arise from these plants and animals, evolution and physics, how can we mentally, seemingly create these mathematical concepts? That's a really deep question. So we'll leave the physicists and the mathematicians and close with the vision of an English poet, painter, and mystic, William Blake, and his painting, Ancient of Days. So this is William Blake, and I love this picture, so it just says a lot symbolically. And his poetry, "I see a world in a grain of sand, heaven in a wildflower, and hold infinity in the palm of your hand, and eternity in an hour." So all of those are good. Now, what I'm going to try one thing to do and ask questions that I'm just going to have going on. If this works, Bob. And taskbar in the bottom. My taskbar is not coming up. So while I answer some questions, Bob's going to, I've
Well,
got.
first of all, let's give Dr. Paulson a round of applause.
Oh, so we'll do questions, but then what I'm put up here while you're going or doing chairs and stuff is a computer. I'll cut into it a computer of one of the fractal formulas that it just goes on. So you watch it, and then you see it just kind of zooms in, and then it zooms in, and it's the same, and it keeps going. So you just kind of watch that for a couple minutes, and I think you're going to be blown away.
Okay.
Okay.
Questions? Hard to know where to
Oh, that's not a good sign.
hard to know where to start, isn't it?
Not a good sign.
Oh,
So are you saying that there are no plants with 4 petals? Flowers with 4 petals?
No, I'm saying that I haven't gone around and I don't know the answer to that question. I've not seen flowers many with 4 petals, and I'm sure you go around and there's some that have weird things, but I just find it so interesting that
Mandelbrot set. The Mandelbrot
4-leaf
set
clover,
was
I guess,
discovered
yeah.
by Benoit
But most of
V.
them are what?
Mandelbrot.
3-leaf
It
clovers.
generated-
So I looked at 4-leaf clover as an aberration that got screwed up and won't go on and reproduce.
other questions?
Yeah, great.
Oh boy, we've got music and everything, I guess.
So Bob's
Other
gonna try to
questions?
show- yeah. So this is going to be a fractal, just showing you what it looks like going into a fractal. Well, eventually Bob will get that. Yeah, other questions? We can see it up here pretty neat. But if we get this, I think it shows, remember this is math that's done this, that's make that. And it's fractals that we talked about. And it's repeating, and it's like, it gives me the closest gut feeling of infinity that I can have. When I look out at my telescope, yeah, you can see that looking way out in the universe, but this thing is like looking the other way, and it's like, wow, that's pretty wild. Ooh, we're getting close here. Yeah, okay, if you can bring that one up. Yeah.
curves in on itself, making an incredible,
Yeah.
intricate structure. Within the
Oh, that's good.
Mandelbrot set,
I
we
just
can
leave it
find
there.
a near-perfect copy of the entire thing.
Let's just,
And look, here's another. But it's a little crooked. No one designed this mathematical creature. The order, structure, and beauty we find is simply embedded in reality. In this image, I see God. We live in a world of which beauty is an inherent, inseparable part. Think for a second. If no one created this image, how could it be so beautiful? How could it be that way? It just is. Sometimes there is no reason why.
Yeah.
isn't that
Thank-
cool?
Thank you again.
Yep.
Yes, let's.
Hi, I'm going to talk
I
about the
told
myth.
I told Dr. Paulson that of the shapes that you got to choose from, what shape you liked the best, and the one that was most people preferred was the golden ratio. I was in the 2% group, and I don't know what that means. I'm just revealing that to you. Next week, Professor Carla Erickson is going to come and talk with, I think, 6 or 7 of her students in their ongoing research on artificial intelligence and what it means for us in probably the near future. And so please come back next week. And if you can help with chairs, so much the better. See you. Thanks.